So this is a review for exam 1, and I just emailed out and posted on Blackboard a review sheet. Let me just show you what it looks like. Let me go to share screen. Yeah, there it is. So this is review for exam 1, which is on Wednesday. And the simplest statement is that everything we covered, you're expected to know. There's certain very important theorems. Here are 6 of them. The division algorithm, the fact that an additive subgroup of the integers is a set of multiples of a fixed positive integer. The fact that the greatest common divisor of a set of integers is an integral linear combination of them. Euclid's lemma on divisibility that says, among other things, that if a prime divides the product of 2 integers, it divides at least one of them. There's the fundamental theorem of arithmetic. Every positive integer is a product of primes in an essentially unique way. And there is Euclid's theorem that there are infinitely many primes. So these are absolutely essential facts from number theory. You need to be able to solve problems like this to use the division algorithm. I mean, that's just what you learned in elementary school. It's long division. How to compute the m-adic expansion of an integer. The Euclidean algorithm to compute the greatest common divisor of 2 numbers. The Euclidean algorithm to compute the continued fraction. The Euclidean algorithm to write the greatest common divisor of A and B as an integral linear combination of them. How to use the Sieve of Varatosthenes. How to factor an integer. There's certain definitions you need to know. A divides B, prime number, composite number, greatest common divisor and least common multiple, and the definition of a group and a subgroup. So, yeah. So anyway, this sheet is posted on Blackboard, and I also emailed it to everyone, so it's in your email right now. Any questions about this?
Good morning, Professor.
Morning.
I have a question. What would be the format of the exam? How are you gonna take the exam?
The format of the exam?
Yeah.
So at 9 o'clock, you log on to Blackboard. The exam will be posted in the assignment section. You take the exam. You can print it out or not, that's up to you. But then, with paper and pen or pencil, you solve the problems and prove the theorems. And then you take your work and you use a printer that you can scan, or if necessary, your cell phone to take photographs of each page, and you make basically a PDF file of the exam pages, and you upload them to the assignment section of Blackboard, just the way you do with your homework, and I grade it. So the exam starts at 9 and it's over at 11.
Okay, good.
So what can we do? So congruences, we started to talk about that on Friday, but congruences will not be on this first exam. But they will obviously make up a large part of the rest of the course.
Professor?
Yes.
And what would you say that is the level of the proof that will be in? Because like in the homework, there are some proofs that are very rigorous.
Right. So they won't be anything like a homework problem where you have as much time as you need to do it. So there will be some proofs, but they'll be fairly simple compared to some of the homework problems.
Oh, okay, that's good. Thank you, Professor.
Mhm. Any homework problems you would like me to go over, or? Let me take a look at some of the homework here, just to do a few problems, if you like, kind of warm up.
Professor,
Yes,
I will have some questions about the proof that includes dealing with mod. For example, like maybe 6 from section 2.1,
section 2.1.
question 6. Or maybe 5, because I think just 6 is just a general version of the question 5.
Oh, okay, so section 2.1, number 5, remember the basic definition, A is congruent to B mod M, means that M divides the difference A minus B, or A minus B is M times Q for some integer Q. So we want to show, and what is called a complete set or a complete system of residues modulo M is a set of M integers, R1, R2 up to R sub M, such that every integer, A, is congruent to R sub I mod M for some I between 1 and M. So for example, 0, 1 is a complete system or set of residues mod 2, because for every integer n is congruent to 0 mod 2 if n is even, and n is congruent to 1 mod 2 if n is odd. So modulo 2, 0 and 1 is a complete system of residues. 14 and minus 3 is another complete set of residues mod 2, because again, for every integer n is congruent to 14 mod 2 if n is even, and n is congruent to minus 3 mod 2 if n is odd. So for any modulus M, there are many, in fact, infinitely many different complete sets of residues. So mod 2, the most natural set of residues to choose is 0, 1, but any two integers, one of which is even and one of which is odd, is another complete set of residues. So that's the definition of a complete set of residues. And what we want to prove in problem 5 this is just another way of stating the same thing, that if you take the even integers from 0 to 16 is a complete set of residues modulo 9. So what that means is if you look at the 9 congruence classes 0 through 8, every integer is congruent to one of these. And I have to show each of these is congruent to one of these 9 numbers. So obviously 0 is congruent to 0 mod 9. That's in the set. 2 is congruent to 2 mod 9. 4 is congruent to 4 mod 9. 6 is congruent to 6 mod 9. And 8 is congruent to 8 mod 9. Right? So So 0, 2, 4, 6, 8, yeah. But 1 is congruent to 10 mod 9. And 3 is congruent to 13 mod 9. And 5 is congruent to 14 mod 9. And 7 is congruent to 16 mod 9. So every integer from 0 to 8 is congruent to exactly one of the numbers in this set. And every number is congruent to 0 through 8 mod 9.
Professor.
So every integer is, so this is a complete set of residues mod 9.
Professor.
Yes.
For 3, you say that it was congruent to 13.
Oh, sorry, 11. Sorry, 12. 12.
Okay.
Yeah. 1 is congruent to 10, 3 is congruent to 12, 5 is congruent to 15, and 7 is congruent to 16. So every integer is congruent to 0 through 8, and every integer 0 through 8 is congruent to one of the even numbers from 0 to 16. So this is a complete set of residues mod 9. That's what we were asked to prove.
But so what happened as you like increase it? Because it's for every entity, it's not like from 0 to infinity, like.
Well, sure, but so let n be an integer, right? So if you divide n by 9, n is 9q plus r, where r, the remainder is between 0 and 8, right? So n is congruent to r mod 9, but r is congruent to one of these numbers mod 9, right? Every number 0 to 8 is congruent to one of these. Every n is congruent to something between 0 and 8. So every integer is congruent to one of these.
Oh, okay, thank you.
Right? It has to do with the fact that congruence is a transitive relation. If A is congruent to B mod M, and B is congruent to C mod M, this implies A is congruent to C mod M. All right. Other questions about congruences, for example? Let me look at some of the problems in section 1.5. This is page 35. For example, number 10 and number 11. So number 10 is to prove pi of n, which is the number of primes p that are less than or equal to n, we want to prove that pi of n is less than n over 2 for n greater than or equal to 8. So first, if you take the numbers up to 8, how many are primes? 2, 3, 5, 7. So pi of 8 is equal to 4, which is 8 over 2. So this is true for n equal to 8. Pi of 9 is also equal to 4. So pi of 9 over 9, that's 4 over 9, is certainly less than 9 over 2. Oops, sorry. I don't want the ratio. So pi of 9 is still 4, which is less than 9 over 2. And pi of 10 is still 4. So pi of 10 is equal to 4, which is less than 10 over 2. And so suppose, let's say n is odd. N is at least 8. And pi of n is less than n over 2. So n plus 1 is even, and n plus 1 is composite, it's not prime. So pi of n plus 1 is the same as pi of n, which is less than n over 2, which is less than n plus 1 over 2. N plus 2 is odd, maybe prime, maybe composite, we don't know. So all we can say is that pi of n plus 2 is at most pi of n plus 1. Because as you go from n to n plus 1, there's no more prime. And n plus 2, maybe it's prime, maybe it's not. So pi of n plus 2 is at most pi of n plus 1. And pi of n is less than n over 2 plus 1, which is n plus 2 over 2. So if n is odd, so n odd, pi of n plus 1 is the same as pi of n, is less than n over 2, is less than n plus 1 over 2. So if this is true for some odd number n, it's true for n plus 1, and it's true for n plus 2. So then you look at, so by induction, it's always true, keeps going. Right? This argument makes sense? I mean, basically all it's saying is, if you take two numbers, one is even and one is odd, and these are bigger than 3 even, at most, one prime, namely the odd one. Maybe it's prime, maybe it's not. So once you're up to a certain point n, if you look at the next two numbers, at most one of them is prime. So at least half of every pair of numbers is prime, and that's how you get the result. And problem 11 is very similar. We want to show that pi of n is at most n over 3 for n greater than or equal to 33. Let's see. What are the primes up to 33? 2, 3, 5, 7, 9, 11, 13, 17, 19, 23, 29, 31. Oops,
Those are
not
not
9,
as
excuse me.
Yeah.
2, 3, 5, 7, 11, 13, 17, 19. Yeah. So pi of 31 is 11, which is bigger than 31 over 3. And pi of 32 is still 11, and it's bigger than 32 over 3. But pi of 33 is 11, is exactly equal to 33 over 3. So for n equal 3, for n equal 33, pi of n equals n over 3. And we want to show that this inequality holds for every number greater than or equal to 33. And the idea is very simple. Like, for example, if you take the next three numbers, 34, 35, 36. So three numbers in a row, one is even, so it's not prime. One is divisible by 3.
Bless you.
So it's not
Bless you.
prime. Right? So suppose for some k, at least 11, pi of 3k is at most 3k over 3, or k. So let's see, so what can we say? What are the next three numbers going to be? 3k plus 1, 3k plus 2, 3k plus 3. And this is 3 times k plus 1. So this number is not prime. Now, if this number is even, if this is even, then this is also even. So it's not prime. So at most one of these three numbers is prime. And if this number is odd, this number is even. So it's not prime. So in any three consecutive numbers, at most one of them is a prime. So pi of 3k plus 3 is at most pi of 3k plus 1, which is at most k plus 1, which is 3k plus 3 over 3. So this statement is true, certainly, for all multiples of 3. And then you have to look at this a little bit more closely. Like, suppose this is true for pi of 3k. What about pi of 3k plus 1? Yes. Anyway, but this is certainly the idea. And If you can almost stop at this point, but if you really want to do it correctly, you have to look at the cases where n is 3k plus 1 or 3k plus 2 as well.
Professor, I don't have a specific question, but when I'm looking at, just your review sheet, do you mind doing a problem about using the sieve of Varatosthenes to compute the prime?
Sure.
Given, thank you.
Yep. Well, so this takes a lot of writing. So let's say, find the primes up to 30. Okay. So you have to write down all the numbers from 1 to 30. There they are. Now the square root of 30 is between 5 and 6. And if n is less than or equal to 30 and composite, then n is divisible by a prime less than or equal to the square root of 30. And the primes less than or equal to the square root of 30, that means less than or equal to 5. They're 2, 3, and 5. So here you have the numbers up to 30. 1 is not a prime, so we cross it out. The first number that's not crossed out is 2. 2 is a prime. But then you cross out all the multiples of 2. No, let me use. Cross out all the multiples of 2. That's all the even numbers bigger than 2. Now the next number that's left that hasn't been the smallest number after 2 not crossed out is 3. So that's going to be a prime. And then you cross out all the multiples of 3 bigger than 3. 6, 9, 12, 15, 18, 21, 24, 27, and 30. And then the next number that hasn't been crossed out is 5. That's a prime. And we cross out all the multiples of 5. 10, 15, 20, 25, and 30. And every number left has to be a prime. So the numbers left are 7, 11, 13, 17, 19, 23, and 29. So the primes up to 30 are 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. Right? There they are. So this is the sieve of Varatosthenes. We cross, if you want the primes up to n, compute the square root of n and cross out the multiples of all primes less than or equal to the square root of n. In this case, the primes less than or equal to 5, 2, 3, and 5. So you cross out all the multiples of 2, 3, and 5, and you'll get all the primes up to the square root of n. That is the sieve of Varatosthenes.
Professor,
Yeah,
and the part where you say compute the standard factorization of a positive integer, that's just a breakdown of some integer into the prime numbers, right?
yes, yeah. I mean, here, I'll make up a number,
Maybe 30.
785. So you just need to factor it. So it's obviously divisible by 5. So this is 5 times 157. And I don't know, this is not divisible by 2 or 3 or 5 or 7 or 11. So this is the prime factorization. These are both primes. Let's look at another problem in section 1.5. I had assigned number 13. So if you have the sequence of prime numbers, P1 is 2, P2 is 3, P3 is 5, and so forth. This is just the primes in increasing order. We want to prove that the nth prime is less than this double exponential 2 to the 2 to the n minus 1. And I give a hint, which is use the idea in Euclid's theorem that there are infinitely many primes. So if you take the product of the first n primes in this list and you add 1, this is a number not divisible by any of the first n primes. So it's divisible by some prime. So that p to the n plus k, let me just call this capital N for the moment, that p to the n plus k divide n, right? So this is a positive integer bigger than 1. It's a product of primes. It's not divisible by any of the first n primes, so it's divisible by some bigger prime, n plus k, the n plus kth prime, say. So p sub n plus k is less than or equal to n, which is p1 p up to p sub n plus 1. And the primes are getting bigger. K is at least 1. So p sub n plus 1 is less than or equal to p sub n plus k. And suppose, so we're going to do this by induction. For example, when n is equal to 1, p1 is 2, and 2 to the 2 to the 2 minus 1 is 2 to the 2 squared is 4, and 2 is less than 4. So this is certainly true. Sorry, 2 to the 2 to the 1 minus 1, which is 2 to the 2 to the 0, which is 2. So it's certainly true for n equal 1. We just want to check for n equal 2. P2 is 3. And 2 to the 2 to the 2 minus 1 is 2 to the 2, which is 4. And 3 is less than 4. So assume that this statement is true for the first n primes. So what can we say about this? This is less than or equal P1, 2 to the 2 to the 1 minus 1, P2, which is less than 2 to the 2 to the 2 minus 1, P3, which is less than 2 to the 2 to the 3 minus 1, up to, up to P sub n, which is less than or equal to 2 to the 2 to the n minus 1 plus 1. So what this is equal to, this is 2 to the first power, 2 squared, 2 to the 2 squared. Oops, let's see, 1 minus 1. This is 2 to the first power, 2 to the second power, up to 2 to the 2 to the n minus first power plus 1. But you know rules of exponents, when you have powers of 2 multiplied together, this is 2 to the sum of the exponents. And the sum of the first n powers of 2 is exactly equal to 2 to the 2 to the n minus 1 plus 1. Which is 1/2, well, which is certainly less than 2 to the 2 to the n plus 1, and n is the same as n plus 1 minus 1. So the statement is true. If it's true for the first n primes, it's true for the n plus first as well. And that's the proof.
Professor, the exam will be this Wednesday.
What?
The exam will be this Wednesday.
Yes.
Okay.
Yeah. It's on the syllabus, I believe, or the lecture and homework schedule. It says Wednesday, October 6th, exam 1 on chapter 1. Yep.
No problem. Thank you, Professor.
Any other questions from chapter 1 that you might like me to do? All right, well, let me do some problems on congruences. So in chapter 2, section 2.1, number 1. Compute the least non-negative residue of 10 to the k plus 1 modulo 13 for k equal 1, 2, 3, and 4. So if n, for every integer n is always equal to, if you divide by mq plus r, where r, the remainder, is between 0 and m minus 1. So n is congruent to r mod m, and r, which is in this set, is the least, the smallest non-negative residue mod m. These are all non-negative integers. So when k is equal to 1, 10 to the k plus 1 is 10 plus 1 is 11. So 10 to the k, so 10 to the 1 plus 1 is congruent to 11 mod 13. This is the least non-negative residue. When k is 2, we have 10 squared plus 1, which is 101. If you divide 13 into 101, this goes 7 times and leaves a remainder of 10. So this is congruent to 10 mod 13. That's the least non-negative residue. When k is 3, 10 cubed is plus 1 is 1001. Again, we can do it this way. You can always divide 13 into 1001. This goes exactly evenly. This is congruent to 0 mod 13. And when k is 4, 10 to the 4th plus 1 is 10,001. Let's see, let's divide 13 into 10,001. This goes, I think, 9 times. 9 3s are 27. So it looks like this leaves a remainder of 4. This is congruent to 4 mod 13. But I'm going to double check this because yeah, I assume that's right. But if another way to do this is a check, let's just check the last one. We know 10 is congruent to minus 3 mod 13. So 10 to the kth power is congruent to minus 3 to the kth power mod 13. So 10 to the 4th is congruent to minus 3 to the 4th. Minus 3 to the 4th power is 81. This is a smaller division, 13 into 81. 6 3s are 1878. So we have a contradiction. Because this says it's congruent to 3 and this says it's congruent to 4. So let me just double check this division. 13 into 10,001, 91, 90. 6 times 13 is 78. This leaves 12, 121. 9 3s. So I'm really puzzled why this doesn't work out properly. Oh, plus 1. 10 to the 4th is congruent to 3 mod 31. 10 to the 4th plus 1 is congruent to 3 plus 1, which is 4 mod 13. So it's correct. So we did this problem in 2 different ways, but of course, we always get the same answer. All right. Any questions about this? So you have to remember or know or look up constantly the definition of a ring. So Z mod MZ, which is the set of congruence classes, modulo M, is a commutative ring. So for example, in number 3, we want to compute the multiplication table. Of Z mod 5Z. So for simplicity, suppose I let A bar be A plus 5Z, this congruence class. So my multiplication table, there are 5 congruence classes, 0, 1, 2, 3, 4. So 0 times anything is 0. So 0, 0, 0, 0, 0, 0, 0, 0. And 1 times everything is everything. This is 1, 2, 3, 4. And 1, 2, 3, 4. That's easy. 2 times 2 is 4. 2 times 3 is 6, which is the same as 1 mod 5. 2 times 4 is 8, which is the same as 3 mod 5. 3 times 2 is 6, which is 1 mod 5. 3 times 3 is 9. So 3 times 2 is 6, which is the same as 1 mod 5. 3 times 3 is 9, which is the same as 4 mod 5. And 3 times 4 is 12, which is 2 mod 5. And 4 times 2 is 8, which is the same as 3. 4 threes are 12, which is the same as 2. 4 times 4 is 16, which is the same as 1. So this is the multiplication table for the ring of congruence classes, modulo 5. What about the congruence classes modulo 6? So we have, so again, we'll let A bar be A plus 6Z. So we have the 6 congruence classes, 0, 1, 2, 3, 4, 5. And 0, 1, 2, 3, 4, 5. 0 times anything is 0, so I'm just going to leave out the 0, so just 1 through 5. So if you multiply anything by 1, it doesn't change, so this is still 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. Modulo 6, 2 times 2 is 4. 2 times 3 is 6, which is 0. 2 times 4 is 8, which is 2. And 2 times 5 is 10, which is 4 mod 6. 3 times 2 is 6, which is 0. 3 times 3 is 9, which is 3 mod 6. 3 fours are 12, which is 0 mod 6. And 3 fives are 15, which is 3 mod 6. 4 twos are 8, which is 2 mod 6. 4 threes are 12 is 0. 4 times 4 is 16, which is 4. And 4 times 5 is 20, and 20 is congruent to 2 mod 6. 5 times 1 is 5. 5 times 2 is 10, which is 4 mod 6. 5 times 3 is 15, which is 3 mod 6. 5 times 4 is 20, which is 2 mod 6. And 5 times 5 is 25, which is 1 mod 6. So this is the multiplication table, modulo 6.
Professor,
Yes.
I have a question because I had a little bit of a confusion because I don't remember. I'm not sure if I'm wrong, but this is similar to Cayley table, right?
So it's similar to what?
Cayley tables.
Well, yeah, I mean, the Cayley table for a group, is that what you mean?
Yeah, but I was confused because I remember like that the rows have to have like every single element, and since I saw
Right. So the point here is that multiplication of congruence classes does not form a group.
Oh, okay, that's why you
Right.
get repeated elements, right?
Now, modulo 6, modulo 5, if you take the non-zero congruence classes, so let's just cross out the zeros, then this is the non-zero congruence classes mod 5, they do form a group. And you'll see in every row and every column, you have some permutation of 1, 2, 3, and 4. This is for m equals 5. Because the non-zero congruence classes mod 5 do form a group under multiplication. But for m equals 6, the non-zero congruence classes do not form a group. So you have all of this, which is very strange if you think about groups.
Yeah, okay, that makes sense. Thank you, Professor.
Yeah. Modulo 6, if you just took 1 and 5, those two congruence classes form a multiplicative group. 1 times 1 is 1, 1 times 5 is 5, 5 times 5 is 1. So just this would be like a group with 2 elements, but the set of all the congruence classes modulo 6 do not form a group under multiplication.
And that's true for all even congruent classes?
Well, it certainly is true that for so
Like for example, if you do the 8, the 10, you're gonna see that there's no group included.
So Z mod MZ is the ring of congruence classes. And this is an additive abelian group. If you take Z mod MZ star, what this means is the set of all congruence classes A plus MZ, where A and M have greatest common divisor 1. And this is a multiplicative group, always. But for example, what is Z mod 6Z star? It's all the A's, all the congruence classes that are relatively prime to 6. There are only 2 of them, 1 plus 6Z and 5 plus 6Z. Because if you look at, for example, 2 plus 6Z, 2 and 6 is greater than 1. It's not equal to 1. If you take a prime P, Z mod PZ star, this is all the non-zero congruence classes. 1 plus PZ, 2 plus PZ, up to P minus 1 plus PZ. So for a prime P, the non-zero congruence classes always form a multiplicative group. But if you have M a composite number, that's not true. Only this subset, only the congruence classes A plus MZ, where A and M are relatively prime, that always forms a group. And we'll prove that later in this chapter.
Okay, Professor, thank you.
Let's look at in section 2.1, number 10. Prove A cubed is congruent to A mod 6 for every integer A. Well, all that says is A cubed minus A, we have to show that's divisible by 6. this is a times a squared minus 1. A squared minus 1 factors a minus 1 times a plus 1 times a. And here we have 3 consecutive numbers. So one of them is even, one of them is divisible by 3. So the product is divisible by 2 times 3. For example, 3 cubed minus 3 is 27 minus 3 is 24 is 6 times 4. 3 to the 4th minus 3 is 81 minus 3 is 78, which is 6 times 13. 3 to the 5th, sorry, this is correct, but that's irrelevant. A cubed minus a. 4 cubed minus 4 is 64 minus 4 is 64, is 6 times 10. 5 cubed minus 5 is 125 minus 5 is 120, is 6 times 20, and so on. That's what it is. Okay. All right, I don't want to get.
Professor, can you do please question 9 from the same section?
This section 2.1?
Yes, question 9, please.
Okay, I'll
Thank
try
you.
to do it. Hope it's not too hard. Section 2.1, number 9. So we take an even number, m. M even means it's 2 times q. And we want to show that every integer n is congruent to r mod m for r, one of the numbers from minus q minus 1 up to q. So let's just take an example to see what this means. Example. Suppose I take m equal to 8, which is 2 times 4. So q is equal to 4. So I claim r is in the set from minus 3 up to 4. These 8 numbers, that's the set. From minus q minus 1, that's minus 3, up to q equal 4. So we have 0 is congruent to 0. This is all mod 8. 1 congruent to 1, 2 congruent to 2, 3 congruent to 3, 4 congruent to 4. Those are all numbers in this set. 5 is congruent to minus 3 mod 8. 6 is congruent to minus 2, and 7 is congruent to minus 1. All mod 8. So in this example, we see the statement is true. So how do we prove this in general? So for r between 0 and q, r is congruent to r mod m, right? It's like for these numbers, they're already in the set. So we only have to consider numbers r from q plus 1 up to 2q, which is equal to m. But so if r is between q plus 1 and 2q, then r minus m actually, I only have to go up to 2m minus 1. m minus 1, which is 2q minus 1. So r minus m is less than or equal to, let me just try and do this legibly. So for 0 up to q, everything is okay. Those numbers are already in this set. So we only have to consider numbers r from q plus 1 up to 2q minus 1 or m minus 1. So if q plus 1 is less than or equal to r, if I subtract m, which means I'm subtracting 2q, what I have over here is 1 minus q or minus q minus 1. And r is at most m minus 1. So this is at most m minus 1 minus m, which is minus 1. So in this range from q plus 1 up to m minus 1, r is certainly congruent to r minus m mod m, because the difference r minus m is just m. It's m times 1. And every number in this range is congruent to r minus m, which is one of the numbers from minus q minus 1 up to minus 1. Right? And that's the proof. I mean, you have to spend a certain amount of time thinking hard about understanding the notation, the method of proof, but if you look at this example, you see exactly what's going on. Any other questions I should go over? All right, then we will quit for the day. I will make sure I have an office hour tomorrow, tomorrow afternoon, probably, if you have any last minute questions before the exam. Okay.